Today we'll be talking about the new ATB-calc open source tools that we released in August. Our agenda for today includes an introduction and overview, including why the ATB and an overview of the Electricity ATB. Then we'll get into the ATB-calc software, including first-time setup, using ATB-calc to calculate LCOE and modify the ATB data. Then we'll do an introduction to the System Advisor model and PySAM software, which is what ATB-calc utilizes for some of its financial case development. And then we'll do a demonstration of how to use ATB-calc to adjust the financial assumptions for new tax credits in the Inflation Reduction Act. And then we'll have time for questions and comments. So to kick things off, why does NREL produce the ATB? Ever-changing technologies can result in conflicting reports of technology progress based on inconsistent and often opaque assumptions. A single data set is needed to credibly and transparently assess the evolving state of energy technologies in the United States, and the ATB enables understanding of technology cost and performance across energy sectors and thus informs electric sector analysis nationwide. We'll do an overview of the Electricity ATB project here. There's also a transportation ATB available at atb.nrel.gov. ATB anchors key DOE and national lab analyses, including tools like the resource planning model, the regional energy deployment system, and the system advisor model. Important scenario analyses have used ATB projections, including the recent report on evaluating the impacts of the Inflation Reduction Act and bipartisan infrastructure law on the US power system, LA 100, the annual standard scenarios, and many others. Now in its 9th year, the ATB is frequently used by planners, academics, analysts, and others. We have some examples of users on this slide, and this is not a comprehensive list. There's a lot of ATB users out there. And as mentioned previously, the ATB data are inputs for the standard scenarios. So we start with the cost and performance assumptions for renewable and conventional technologies in the ATB. And then those are run through the READS model at NREL in order to form the standard scenarios, which is an ensemble of future scenarios for the US electric power sector. The ATB includes a suite of products. The main ATB webinar in July covered the spreadsheet and the web app. Today we'll be focused on open source data and code, in particular the new ATB-calc GitHub repository. So what is in the ATB? The ATB provides cost and performance data for the electric generation sector that includes metrics such as capital expenditures, operation and maintenance costs, and capacity factor. We provide those for every year between our base year, which in the 2023 ATB is 2021, out through 2050. And then we utilize those in order to calculate LCOE. This is the list of technologies covered in the ATB. For more depth on these, I'd recommend the main ATB webinar from July, but note that we did add some new technologies specifically around carbon capture and storage and retrofits for CCS in 2023. The methodology for the ATB includes 3 steps. We define the resource bins for each technology, which groups the range of resources for the contiguous United States into bins with common resource quality and characteristics. So that can include wind speed or solar irradiance, or we develop representative plants based on things like carbon capture rate or type of geothermal system. We then use those bins to develop cost and performance data, which develops the base year and projected values across 3 scenarios for the metrics included in the dataset, and then use those to calculate LCOE along with some financial assumptions. The summary of bins is listed here and the distinguishing characteristics between the bins for each of the technologies represented. An example of how the bins are generated is on this slide for land-based wind. So we use resource data throughout the contiguous United States in order to develop a supply curve. The bins typically have a little bit more resolution at the higher end of the wind speeds where the wind resource is more likely to be developed, and then a little bit wider bands of possible wind speeds further down the supply curve. Once we have those groups of representative technology resources defined, we can develop cost and performance data. So the base year of 2021 is informed by market reports, market data, and bottom-up modeling. Projections generally rely on bottom-up modeling and published studies, and are qualitatively harmonized to 3 scenarios of future technology innovation. That includes the conservative scenario, which is today's technology with little innovation, continued industrial learning, decreased public and private R&D. The moderate scenario assumes widespread adoption of today's cutting edge, the expected level of innovation, and that current levels of public and private R&D are maintained. And the advanced technology scenario assumes market success of currently unproven innovation, new technology architectures coming into the market, and increased public and private R&D relative to current levels. This summarizes the source of base year costs. These are typically market reports put out by NREL or other national labs, which summarize the data for that base year. And we have to go 2 years into the past for the base year in order to get time for these reports to be peer reviewed and published. And then we use those to calculate the levelized cost of energy. Since this is one of the core features of ATB-calc, we'll be spending a little bit more time on this slide than we usually do. So the levelized cost of energy includes a fixed charge rate, which summarizes the financial assumptions across our 2 financial assumption cases, capital expenditures, and fixed operation and maintenance. And then those are all divided by a net capacity factor, which represents the average generation over the life of the system, in order to get things in units of dollars per megawatt hour. And then we can add those up with variable operation and maintenance costs, the fuel cost, and a discounted production tax credit in order to come up with the levelized cost of energy for a single year for a single technology. Going into a little bit more depth on what goes into this fixed charge rate, these summarize the equations that are in ATB-calc. There are additional equations, particularly for the weighted average cost of capital, that are still in the ATB Excel spreadsheet, but this sort of gets the high-level idea of what's needed to come up with that fixed charge rate. So the fixed charge rate is solved for by multiplying the capital recovery factor and the project finance factor. The capital recovery factor takes the weighted average cost of capital and discounts it to present value according to the cost recovery period. The default cost recovery period in the ATB is 30 years, but we provide options in the spreadsheet in ATB-calc for 20 years or the technical life of a technology. The project finance factor includes the tax rate, the present value of depreciation, and the investment tax credit. And note that the investment tax credit term shows up twice because the investment tax credit reduces the depreciation basis when it is used with a technology. So a little bit more detail on the financial cases presented in the ATB. We have 2 financial cases. The R&D case represents technology-specific changes to debt and interest rates, return on equity rates, and debt fractions to reflect the effects of R&D on technological risk participation, but then it holds all of those values constant, such that you can see the effect of technology improvement alone. Because we're holding those things constant, we have to exclude the effects of tax credits. The markets and policies case uses those same interest and return on equity rates, but then adds in the effect of tax credits from the Inflation Reduction Act of 2022. And the charts here show one case for land-based wind, so you can see the impact of the tax credits on LCOE. Within the financial cases, the base year, as mentioned previously, is 2021. That also means the dollar year is 2021. So all data in the 2023 ATB that have units of dollars are reported in 2021 real dollars. The markets case includes the Inflation Reduction Act tax credits. We assumed that the tax credits phase out in 2038 based on when the 2022 standard scenarios mid-case hit a 75% reduction in greenhouse gas emissions from the electricity sector. The default tax credit assumptions, which we'll be showing how to modify towards the end of the presentation, assumes that the labor requirements are met for projects, but no bonus credits are received. So that's a 30% investment tax credit and a $27.50 per megawatt hour production tax credit deflated to 2021 dollars, since that $27.50 is a 2022 dollar year value. And then within the ATB spreadsheet, the year of the column is the commercial online date. So generally, we assume that most technologies, offshore wind being the exception, which is a bit longer, receive 4-year safe harbor. And then there's a phase out schedule for the credits. So in practice, once you add up that safe harbor and the phase out schedule, that means the credits are first reduced for most of the utility scale technologies in 2024. And then we used the system advisor model to calculate the debt fractions, going from a debt service coverage ratio to a debt fraction, which for the first time this year includes annual calculations for the market's case. And we'll get into how that works a little bit later. So with that, we'll get into a demonstration of the ATB-calc software. So I mentioned that this was open source on GitHub. So this is the URL for ATB-calc right here. Typical with a GitHub repository, we have a couple of different folders for the code and examples and tests, and then links to the ATB website in order to access and download data, and then some more details of how to run the code and install the software that we'll get into in a minute. Note that the ATB data is not maintained within this repository. We still want you to go to the main ATB website to download the data, so I'll go ahead and do that now. So when you land on atb.nrel.gov, you see this landing page, which talks about the ATB project in general. ATB-calc has tools for the electricity project, so we'll click on electricity, and then we'll click on data here. And then what we need in order to run this is this 2023 ATB Excel workbook. So I'll just click on that, and that's going to automatically open up this download link, which I already downloaded this prior to the webinar. So you would click save, but I'm going to click cancel right here. Then one other note is that there are a lot of other different data sets that we provide in addition to the Excel workbook. So if I open this download all related data link in a new tab, we can see some of the other types available on ODI. And that includes the Tableau workbooks, the parameter data for more detailed parameters for individual technologies, and the Electricity ATB data lake. So these are all different ways to access the ATB data. Just ATB-calc focuses on this Excel workbook. So with that, then we need to get to downloading and setting up the requirements for the software. So if you're familiar with Git, you can find the clone link here in the usual space. There's also an option to download a zip if you're not a Git user. At this stage, I'm going to assume that you already have Python, a package manager, and a virtual environment of some kind, virtual env or conda, either will work fine, installed on your computer. If you're watching the recording later and you don't have that done, this would be a good time to pause and do that. So I will share this window, and as soon as I get it dragged over to the correct screen. And so we can see here that I have ATB-calc checked out in a folder. And then I have already set up an environment for ATB-calc to run in, which the instructions for that are located in the main README. So we've set up a requirements.txt file that you can just use with pip install-r, and that will get all of your requirements in order to run the code via the command line installed into your virtual environment. We've left out 2 additional requirements for the demo just because they tend to be a little bit hefty and we wanted to keep requirements.txt a little bit light. And that is Jupyter Notebook. So you'll probably want to install Jupyter if you're following along with the demo. And then the examples also require matplotlib. And so those are documented in the README of the examples folder. So with all of that done, we can get into this process ATB technology Python or Jupyter journal, Python notebook, and look at how some of this works. So first thing is note that we're going to start with the code in the LCOE calculator folder. And we've set up these classes called tech processors, each of which has all of the information required to get one technology's worth of data out of the spreadsheet, and then do the calculations required to calculate LCOE. All of those are child classes of the base processor class, which if we jump over to that Python file here, this is importing, some of the useful libraries like pandas and NumPy, and some other data from around the code. And then ultimately, what this is doing is fleshing out some of these data frame objects, such as net capacity factor, overnight capital cost, fixed O&M. So this is how this class is storing some of that ATB data. And then there's another set of output data frames, which once we run the processor, this will calculate some of these values, including CapEx and LCOE, and project finance factor, et cetera. So if we go back to this notebook, it just starts by importing all of these processors. So we'll just go ahead and do that. Note that I'm doing this within VS Code. You can run this in whatever Jupyter-friendly environment that you want. And then I have this ATB-calc environment set up here with my Jupyter notebook. And then this is the one step where you actually have to do a slight modification for the code in order to run things. If you're doing this on the command line, you could just specify a command line argument, which is just setting the path to that workbook. So I'm going to pull up that file folder where I downloaded this earlier, and just copy the path to that workbook and then paste that in here. And then I'm on Windows, so I have to escape all of my backslashes. Mac users won't need to do this, but Windows uses backslashes in file folders, so we do. And then we can just run that and get that path set up. So then we have in the next cell some additional setup for the cost recovery period and financial case. So the default within this notebook is 20 years in the R&D case. And then we're just going to set up offshore wind as an example. There's some other additional examples down here if you wanted to run additional or a different technology. And then we have this full workflow notebook if you wanted to process all of the technologies. That takes a few minutes, so we'll just do that here. One thing that I should have mentioned by this point is that when you first open the ATB workbook, Excel opens it in protected mode. The code will not work with the Excel notebook in protected mode, so you have to enable modification of the Excel workbook in order for any of this code to run. But the code will read all of this for you and import all of the data for you into Python. Okay, so what we've done so far with this cell is set up our offshore wind processor, and that loads all of the data out of the Excel workbook for this set of assumptions for that technology. So we can view some of that data already by looking at the metadata for this class. So the processor has metadata including the name of the various technology details for offshore wind. We can see here that there's two subtypes of this technology. So classes 1 through 7 assume a fixed bottom technology, and 8 through 14 assume floating. And then those also correspond to different wind speeds. All of these are utility scale technologies. The ATB also represents some commercial and residential scale. And then we also, new to 2023, have this maturity metric. So a yes in the maturity column means that the technology is currently in operation or under construction in the United States. And a no means that it is not. So we just wanted to provide that little bit of additional clarity on the data for users in this column and in the visualizations. Once we have that data imported, we can run the pipeline. And so this is going to perform all of those calculations. And then we have two test functions here, which make sure that the CapEx and LCOE within the workbook match what Python calculated. So we use this as a little bit of an internal quality check. You're welcome to use it, for your own quality checks as you make modifications to any of the data. We'll comment that out later as we're modifying things in Python. And now that we've got all this calculated, we can view the results. So this just prints the data frame with all of the levelized cost of energy values with the different wind classes and different scenarios across all of the years presented in the ATB. And that's true for every metric that's in that processor class, such as net capacity factor, weighted average cost of capital, and construction finance factor. And then we can use matplotlib in order to generate a plot of the offshore wind LCOE for, looks like, class 1 advanced by the years in the ATB. So that's all fine and good. We've successfully imported this into Python and reproduced the data that's in the spreadsheet. But we might want to modify that data. So as an example, I'll come back up here to the point at which we had the data imported, but nothing calculated. And then I'm just going to look at, so if I look at the variable processor, DF overnight capital costs, that's not how that's abbreviated. Okay. And then I'm just going to increase all of these values with the times equals modifier by 10%. So there's a couple of reasons you might want to do this. This might be a way to account for inflation. So converting the dollar year from 2021 to probably, this is like the middle of 2023. I would expect, once you actually get to 2023 dollars, it might be closer to 12%. If you're using this for that approach, you'd also want to do this for both O&M values and the grid connection cost. Another possible use case is adjusting for regional cost values. You can go to the READS documentation and download what they have for regional cost values for these different technologies and apply those to your ATB data. So if I do that, this is just going to run without printing anything. And then I can rerun the pipeline and get the, eventually here, get the somewhat unsurprising result that the calculated CapEx does not match the CapEx from the workbook. So, I modified the data in Python. I didn't modify the data in the Excel. So this is expected. I'm just going to comment these out, but just wanted to, demonstrate what this error and these standard quality checks look like. So if I run that again with those commented out, then this will rerun the data with those new values. And if you look at this column, it used to be 8542 for that LCOE value. With that increased overnight capital cost, it's now 8987. And then I can come down here and plot the new data with those adjustments made. So this sort of gives you hopefully an idea of the power of doing some of this through Python. I was able to do that relatively quickly. In Excel, I would have had to create a new sheet, multiply all the values, and then rerun all those calculations in Excel, whereas this was relatively quick to make that type of modification. Just wanted to mention, if you are just looking to work with the ATB data in Python and not make any modifications and recalculate LCOE, this Open Energy Data Initiative Open Data Access Tools repository might be more appropriate for your use case. So if you come into here and look at, I think it's examples, there's some example notebooks for how to download the annual technology baseline data from AWS S3. So this is totally your preference if you want to work things on your own computer with the Excel workbook, or if you want to be downloading things from S3. Just wanted to point out some of these other ways to interact with the data via Python. Right, so with that, we will get into the second half of the content here, which talks about how to use ATB-calc along with System Advisor Model in PySAM in order to make some adjustments to the financial assumptions to account for the Inflation Reduction Act bonus credits. So for those of you who aren't already familiar with it, System Advisor Model and PV Watts are free software that enable detailed performance and financial analysis for renewable energy systems. SAM is typically shipped as a desktop application. PV Watts has a web tool and application programming interface for streamlined PV performance calculations. Both are available as a software development kit, and as we'll see in today's demo, the PySAM Python package. These are also open source products available on GitHub, and they both have extensive documentation and user support. The models in SAM are structured into performance and financial models. So the performance models take weather data, system specifications, and losses in order to calculate hourly or sub-hourly power production. And those are then summarized into monthly or annual production metrics or capacity factors. Many of the capacity factors in the ATB are calculated using SAM's performance models via the REV tool. Then SAM also uses those production numbers in a financial model. So that includes things like costs, incentives, financing, and compensation, and calculates outputs like net present value, levelized cost of energy, payback period, operating costs, etc. And it's worth noting that some of the ATB's cost data ends up as the SAM defaults. This is the list of technologies covered in System Advisor model. It ranges from PV, energy storage, wind, geothermal, as well as others, and financial models, including both front of the meter and behind the meter financial models. So we'll be focused on front of the meter financial models today, but all of these are available both in the desktop software and in PySAM. So what is PySAM? PySAM is a Python package that enables you to run the underlying modules that make up a simulation in SAM. So I mentioned those performance and financial models earlier. The code for all of those is available in a repository that we call SAM Simulation Core, or SSC, and we refer to those as compute modules. If you're installing PySAM in your own environment, note that the package name is NREL-PySAM. If you just try to install PySAM, you'll end up with something different. And so we have documentation on how to get that set up with PySAM. Generally, if you're trying to mimic the behavior of a simulation in SAM, you need to chain together multiple compute modules. So you have to have that performance model. There might be some intermediate models that account for things like grid curtailment, and then those financial models such as utility rate calculations or behind or front of the meter financial models. And then PySAM is set up such that that information gets passed down this chain of models. So PySAM and SAM software development kits are exposing these unit models such that they can be customized and embedded into software applications. So for example, there's a certain set of combinations of performance and financial models that we ship in desktop GUI. If there's one that you're interested in, say like community distributed wind, for example, that's not something we don't have we have a community solar model in the desktop GUI. We don't have that sort of financial structure for wind, but that's something that you can put together in PySAM. And then an important caveat, if you're running PySAM, it does not contain all of the features of the SAM GUI. So I think probably the classic example of this is if you're modeling a detailed PV system, and you change the number of strings in parallel, the system capacity variable does not get updated by default in PySAM, whereas it does in the GUI. So generally our recommendation is as you develop your cases, do things in the GUI first, and then use some of the JSON export functions in order to set up your PySAM cases and then modify the necessary variables from there. And there's instructions to do that on how to do that on that documentation link at the bottom of the screen. I mentioned help. So the SAM GUI has a help system built into the F1 key or clicking help in the SAM software. There's also a web version of that available. There's a dedicated long-running user forum where you can find answers to past questions, or you can post your question on the website where the answers will be helpful to anyone on the internet. And then there's also email support. So with that, we're almost ready for a demo. I just want to give a little bit more information on the ATB financial cases. So a lot of the underpinning for the ATB financial cases and the data we're going to be showing over the next set of demonstrations is this report from David Feldman, Mark Bollinger, and Paul Schwab, current and future costs of renewable energy project finance across technologies. So that presented things like interest rates, rates of return on equity, and debt service coverage ratio. We've updated some of the values in that report to account for the recent increase in interest rates that was published in 2020, and interest rates have increased a lot over the last year and a half. But we're still finding that the debt service coverage ratios there are generally consistent with previous assumptions. And so that's what's being presented there. You'll note that the ATB data, if you go into the spreadsheet, presents debt fraction, not debt service coverage ratio. So the key step here that we're going to demonstrate is converting that based on some of the other cost and performance assumptions within the ATB. So we'll start with a demo of the SAM software, which is all the way over here on my other screen. So what I've done for this case is taken some of the ATB data and put it into a generic partnership flip model. So a partnership flip is a tax equity structure where you assume that there's a developer of a project and then a tax equity investor, and they're sharing some of the costs and tax benefits of the project. In general, the Inflation Reduction Act might reduce the use of this type of structure based on the transferability of credits to entities with more tax appetite. We don't have the data yet to know, what the costs of that transferability are going to be. And I think there's some motivation for maintaining these types of structures in terms of the tax benefits of depreciation. So we've kept that model for the 2023 ATB. We'll update it as we do more research, but that's the motivation for partnership flip. The motivation for generic system here, as opposed to one of the technology-specific models, is the ATB has already done the work to boil things down into capacity factor. So I can just take a nameplate capacity and capacity factor here and just get a simple flat generation profile that is perfectly sufficient for the type of calculation that I'm doing. I can incorporate installation costs from the ATB. So what I've done here is I've taken the parameters from the moderate case for land-based wind in 2038 and put the costs and both the capital and operation and maintenance costs into SAM. And then we have some of our financial parameters in order to deal with that partnership flip structure, account for the rates of return on equity, account for the debt service coverage ratio, account for the annual interest rate, account for construction financing. So all of the numbers in here are based either on data available in the ATB spreadsheet or data available in that renewable energy financing report. I've also put in the incentives section that default production tax credit. And so that's in here. That's good for 10 years. And so we can just run this. And this gives outputs. This was run in what we refer to as the investment rate of return target mode. So we're looking for the tax investor to get a certain return based on that ATB rate of return on equity. And then this will calculate the PPA price required for this capacity factor and these costs in order to hit that return. So we see that the investor does in fact hit that return, and the PPA price required is only 2.13 cents per kilowatt hour in 2021 dollars. So obviously this is 2038 data. We expect there to be 15 years of inflation between now and then. But what I want to point out here is that this is a relatively low PPA price, and the SAM models assume that the tax credit, which is providing a significant chunk of the return on investment here, is not eligible for debt service. So as this project decides how much debt or equity it needs to take, it is going to have to account for the fact that those tax credits cannot be used to pay down the debt. So on that basis, it's ended up with this relatively low debt percent of 30.22. I will point out that we tried this with the single owner model as well, and that ended up with even lower debt percentages. So that was part of the motivation for using partnership flip in this model. It got us the expected debt percentages a little bit more organically. So then what we need to do in order to account for the recalculate the financial cases based on any changes to the financial assumptions is basically do what we've done for this SAM case a couple hundred times. So that's again where the power of Python comes in. The ATB-calc package is able to pull the data in from the spreadsheet. So in this case, Excel is providing a nice user interface to make some of these modifications. The ATB spreadsheet has a few definitions and input tabs at the front. It has all of the detailed technology data in the middle. And then eventually, as we get way over to the right here, we get to some of the financial assumptions. So this WACC, or weighted average cost of capital calc tab, has the default financial assumptions for all of the technologies, including these interest rates, the rate of return on equity, the debt fraction, and the tax rate. Anything in purple here is an input, whereas except the tax rate and gray is a calculated value. And so if you have financial assumptions that don't match these that you want to evaluate for your specific use case, you can modify these. And then the step that was missing until now is that modifying these really should require an update to this debt fraction, because as the weighted average cost of capital changes, as the tax credits change, these projects are going to be making different decisions on debt versus equity. So as far as what motivates some of these changes, the Inflation Reduction Act allows for the production tax credit and the investment tax credit to increase if the content of the project is produced domestically, or if the projects are located in an energy community. Additional credits for projects located in low-income communities or on tribal land are also available. And more information on this is available on this White House website here. I will say that ATB-calc will not help you determine what project credits are appropriate for your project, but we are providing this code to help you then, once you've determined what the appropriate credits that you want to analyze are, we're providing this code to sort of help you scale it up so you aren't doing SAM cases for every single year. So once we've determined what our credits are, this tax credits page right here provides inputs for the ITC and PTC. There's nothing to stop you from putting both in here. Just note that projects typically can only receive one. There might be some exceptions to hybrid projects. I think the IRS is still developing some guidance around that. But generally, the recommendation is if one of these has a value, the equivalent down here should be 0. But we just provide both in order to make inputs easier. So let's assume that we're doing a, let's say, a CSP project that's using a significant chunk of domestic content. That first kicks in 2023. So we can change some of these to 40%. And so we'll go through, I want to take these through 2037. And the reason I'm choosing that year is I also want to change the phase out assumption. So let's assume that the electric sector decarbonizes a little bit more quickly than what's represented in the standard scenarios. We can then move some of these credits back a few years. And let's see if we can get this to, yeah, there we go. So this would be basically assuming if I think the earliest that the credits could phase out would be 2032. So then we'll have 1, 2, 3, 4 years of safe harbor. And then I need to move these back one more to account for the phase out. Oops, account for the phase out according to that structure. Let's try that one more time. Okay, I'll just redo these cells right here real quick. So I'm doing equations in these to sort of represent, make it easier to calculate the phase out schedule as the credits changes, which sometimes causes these reference issues. And then I can zero out the rest of these, and so on and so forth. If you were doing this for every technology based on assuming everything was getting domestic content and everything was getting the same phase out, you would need to continue to do that for multiple steps. I'm not going to do that now for time. So then I can save the workbook. And I'm going to go to the README for the debt fraction calculator to pull out this handy dandy Python command that allows us to run the code. So I need to put that there, which didn't copy. Time. Nope. There we go. Okay. And then this has two arguments. One is the input file, which is that ATB spreadsheet. So we'll just go grab that again. And that's going to need to be in quotes. Great. Did that automatically for me already. And then it needs an output file location for a CSV. So we'll grab that as well. We'll just overwrite the one that I made yesterday. Great. And then we can press enter and run this. So then what this is going to do is it's going to open up spreadsheet for all of the different technologies. You can modify that potentially in a Jupyter notebook or similar if you only wanted to do one. Load in all of that data, including the new tax credit assumptions, and then run the SAM model via PySAM in order to calculate those new debt fractions. And then we'll see what the output looks like for that in a second. So I think this is going to take about 2 minutes to run. So I think we can take a question or two while that's running.
Hey, Brian, the team has been hard at work answering some questions via direct chat. But if anyone has one that would be relevant for right now, feel free to send it in and let us know.
Brian, there was a question about, using Python is not the most intuitive, does not appear to be very user-friendly, and why not just do these calculations in an Excel workbook? That did get responded to. Do you have any examples offhand that would be easier to perform in Python than in Excel?
Yeah, so I think maybe this was mentioned in the chat already. One of the advantages I see of Python is a consistency of equations. So in Python, you know that same equation is getting applied to the data every time. Whereas in Excel, especially if you're managing a large file with a lot of people, sometimes those underlying equations, errors can get hidden in there. I think in terms of the intuition and something like that, like I guess some of the I definitely think the example that I showed there does assume some knowledge of Python or pandas. Some of the other potential examples could include Mike, do you have one offhand that you think would be good for that question?
I don't, although will state that quite frequently when the transitioning, programming is generally more complex than using Excel. However, as you start getting into either analyses that need to be run more frequently, or you need to change more variables and do larger, broader, more complex analyses, coding generally starts shining better. If an Excel workbook is adequate for what you need, then by all means, that's probably the better way to go about it. There are definitely, if you have a problem where Excel is not working for you, then the extra effort to learn Python may be justifiable.
Thanks. Yeah, I think that's a great answer. So yeah, happy to talk more about that in a minute, but at the moment we have this updated debt fractions file. And so what this then outputs is for each technology in each case, it has these debt fraction percentages for each of the technologies. And this is the one piece of the puzzle that isn't automated. Which is once you have these, you'll need to copy and paste this entry from here back into the Excel workbook in order to update the debt fractions. So we're doing that for CSP in the market factors case. And so then that goes down on this line. So, if that's something that we on the ATB team have to do this maybe 3 or 4 times a year, so that's not a huge burden to us. If this is something that you would like to see automated, that would be a great example of a feature request. And then right now, all 3 of our cases use the same debt fractions, but one could imagine the cost declines in the advanced and conservative cases generating different debt fractions, and could potentially use this tool in order to come up with different debt fractions for each of those. So with that, again, absolutely encourage you to go to the other resources to figure out what the tax credits should be. Some of the references used here, this manual by Walter Short et al. For the economic evaluation of energy efficiency and renewable energy technologies. I know the date on that is 1995, but this is really the core reference that underpins a lot of what we do in both SAM and the ATB. I'm probably referencing this once a month to answer questions about how LCOE is calculated. So if you really want to get into the weeds on some of that, that's a great place to just get the, some of the core equation development. The REITs documentation includes some of the updates to those equations for tax credits, such as that investment tax credit calculation that I was showing earlier. System advisor model is available as free and open source code. We showed the ATB data on OD already, and then this code is available for free and on GitHub. So with that, thank you, and I think we can get to any additional questions.
Brian, here is another one. Use of ATWAC has some serious shortcomings when applied to a single project rather than a corporation with a large diversified portfolio of projects. It's because the debt equity ratio of a single project changes over its lifetime as the debt is paid off. A better approach is to use the adjusted present value APV method, which separates out the value of the tax savings from debt financing. Has that been considered?
I don't know as we've considered that method for ATB. I think that's a great thing if you wanted to, I can write that down at some point, but we'll look into that as a potential alternative. I will say that there are definitely, I want to emphasize that there's like a couple different ways to calculate LCOE, even within the two projects that I've shown here. So ATB is using this, simplified formula because we're doing this for hundreds, if not over 1,000 different possible projects, right? Because we've got all of the different years, all of the different technologies, all the different scenarios. If you're looking at, single project or single companies, definitely there are going to be different approaches that account for additional considerations. And the models in SAM have this detailed cash flow, which, these values won't actually be constant over time. This is just a simplifying assumption that I've made for this model. But then this gets into detailed annual revenue, detailed annual operating expenses. These values are in nominal dollars, so you can see the escalation for inflation happening through the spreadsheet. And then again, more detailed tax and debt treatment within this software. So I think some of this is underpinning what we do in the ATB, as you can see with that debt fraction calculation. Doing all of this for every project in the ATB would be possible, right? We could definitely set this up with Python, but then we lose some of the user friendliness and transparency of the Excel equation. So that's sort of how we're making this trade-off within this project, and by offering different tools targeted at different users. We'll have a few more minutes for questions if you want to type them into the Q&A box and they haven't been answered already.
Brian, there's a question about importing data into R. And could you quickly go back over getting the CSV data from OD?
Sure, from OD, yeah. So let's see, we have, so there's a couple of options here. So we've got the just direct download links on the submissions page. So we've got both the Excel file that I was showing today, as well as the electricity data lake and some of this parameter data. So for R, you might want to just download these directly. and then open them up using the CSV or Excel files on your computer. Didn't have time to get into the data lake too deeply yet, so now is probably as good of a time as any to do that. So this link here directs the documentation of the ATB data. Let me get to, let's see, view data lake is what I was looking for here. There we go. This will direct you to the S3 buckets on the OD data lake, where you can download both CSV and Parquet data. This folder structure has the different years and historical ATBs, and then this gets you directly to the CSV with all of the calculations already completed. So if you just get to this, you can download this directly using your browser, or set up an API call, which is documented in some of these other OD demonstrations for importing that data into whatever language can read a CSV.
Brian, there's a question about LCOS.
Great. Yeah. So right now, the ATB does not present levelized cost of storage. And the reason for that is because we sort of expect that the storage technologies that we're presenting in the ATB are going to be across a wide variety of use cases, right? So we have pumped storage hydropower, which tends to be from 8 to 12 hours of storage. We have lithium ion batteries, which are from 2 to 10. Right now, a lot of the electricity markets are valuing 4 hours of storage and not much longer because that's the duration of the peak. So because there's, with LCOS, to contrast it to LCOE, right? If LCOE, if you know the location of, say, your solar panels, you can use weather data to get a good idea of how much generation is going to occur in that location. And that will, within certain bounds, be reasonably consistent year to year. Obviously, there's interannual variation, but that's quantifiable. With LCOS, the dispatch strategy is going to change pretty significantly as markets evolve. So the energy term of that is going to vary wildly based on your dispatch profile, the services that are valued by the market at the time, and a whole host of other factors. So that's something that we found difficult to incorporate into the ATB structure, and have sort of stayed silent on it for now. If you think there's a consistent set of storage assumptions that would be super helpful for calculating LCOS, that would be great to hear. But for now, we're leaving that one out of the main ATB data set. I will say that if you're interested in LCOS for a specific project and a specific use case, if we go into SAM here, and let's just pick the default front of meter PV plus battery system, and we run this, and this takes 20 or 30 seconds. So let's see, we've got the default here is a PV array in Phoenix paired with a 4-hour battery with some basic time of delivery assumptions that it's dispatching against. And once this is finished calculating, so we present on this front page the default LCOE that includes the costs of both the storage, solar and the storage. But if we go back into the data tables, we also present nominal and real LCOS for the storage component alone. So all of the storage models in SAM have this, and you can use this to calculate LCOS, putting ATB cost data in here. So that's, this dispatch page will allow you to make some of those charging and discharging assumptions required to calculate LCOS. And the lifetime model will inform battery replacements, which are also an important component of LCOS.
Thank you, Brian. Another question. Do you also use P50, P90 annual solar generation probability?
I think within the ATB, we do not. I think that's sort of like buried back in some of the financial assumptions, right? So like lenders are going to be determining their debt service coverage ratios based on a P90 or a P99. For those who aren't familiar with those terms, that's looking at that interannual variation and like what is the 10% worst probability, or the generation will have a 90% chance of exceeding this within in a given year. So SAM is a great tool to calculate that. You can, for solar, download 23, 24 years of historical data from the National Solar Radiation Database. There's also this, just to continue advertising SAM features here. I'm not going to run this one right now, but the most recent version has this PV uncertainty module, which in addition to the interannual variability of weather, calculates a distribution on key factors, key loss types, which are based on IEA, PVPS, we're getting that wrong, PV performance modeling data. And you can use that to calculate P90 values that include more than just interannual variability. So I will say that that's like way back in some of the ATB assumptions we're incorporating that. I would consider going back to some of the discussion of capacity factor. That's a mean that accounts for degradation over the life of the system, but it is going to be closer to a P50 value than anything else that you would generate via this type of interface. So that looks like we're about at time. So thank you again for your time and attention. Feel free to email with any additional questions. Happy to follow up with questions or feature requests or other questions about how some of these tools interact and similar. Thank you.